So as the title of my talk suggests, we're going to show today how to use machine learning to evade machine learning. And today specifically, we're going to be focusing on evading Windows PE static malware classifiers. So first some context. First, why machine learning and why would evading machine learning be difficult? So one way to think about machine learning model is that it's kind of like a fancy a rule, a sophisticated rule. And in this little cartoon plot, I've represented a bunch of malicious and benign samples by these red and these blue dots, respectively. And I've plotted them in the space of where the x-axis is file size and the y-axis is, the number of registry strings. And then created a Yara rule. And this Yara rule says that if the file size is small enough and there are enough references to strings, then the rule paints this quadrant of my feature space red, which means the rule fires on malware. So machine learning you can kind of think of as a more sophisticated kind of fuzzy rule here. And one that automatically learns from the data what constitutes malicious content or behavior. The patterns it learns also are not obviously constructed by hand. And furthermore, instead of having this sharp and brittle boundary between malicious and benign, the machine learning boundary can be smooth. And this can help it to generalize to never before seen samples and variants. So the question is, can you break machine learning? And what we want to do here is take a malware sample and that when we present it to our model, the model knows that it's malicious with high confidence, like 0.95 in this example. But then we want to, we would love to find some kind of subtle mutations to this malware sample that don't break its format and don't break its function. But when modified and submitted back to the same machine learning model, it now thinks it's a benign sample. So can we evade machine learning? The answer actually is yes. And in fact, in many domains, it can be automated. And it's actually become quite fashionable in machine learning applications of other domains to evade and break machine learning. And perhaps the most well-known of these are these gradient-based attacks, which are demonstrated here by the bus. And here you can think about, the adversary has this bus, which the model knows is a bus with high confidence. But by making very subtle changes, here I've scaled it just so that you can see the noise, or it has been scaled, I didn't do this. But now when presented to the machine learning classifier, it believes it's an ostrich with high confidence. But to your eye, there's no change. The functional format of the image is the same to your eyes. And the takeaway here, I think, for this specific attack and other attacks like it are kind of threefold. The first is that all machine learning models have blind spots. They hallucinate. The second is that depending on the model and depending on the level of access that an adversary has to your model, those blind spots can actually be really convenient to exploit. And the third, I think, is that is a little scary, and that's that in some cases, the adversary doesn't even need your model. In fact, if he can find, this picture of an ostrich if I can find it for my model, there's a non-trivial chance it will also work against your model. And we'll demonstrate some of that today. But first, let me just briefly review sort of the, now not images, but sort of the body of work very briefly about what's been done for attacking machine learning models in information security. And I break this into three buckets. And on these buckets are going to be kind of sorted by what's easiest for the attacker and all the way to what's the most difficult for the attacker to achieve. And in the first bucket, it's where the attacker has full access to your model. He has the source code. He has the model. He knows the weights. And in the case of some specific machine learning models like deep learning, these kind of attacks can be done straightforward. Actually, you can ask the model what would confuse it the most and apply those kind of perturbations to images, and in this case to malware, to achieve some evasion. And I've listed some work done here by collaborators and colleagues and others here for Android malware and for DGA detection. In the middle box, slightly more difficult, is now the adversary doesn't have your model, but he sort of has API access to your model, and he can query it arbitrarily And importantly, he can get a confidence score or some number out that signifies how much the model believes that sample to be malicious. And my colleagues and collaborators at the University of Virginia have developed some methods that can systematically reduce this score over time using genetic algorithms, which I'll just speak briefly to in a few slides. The area that we're interested in today lives in the final box, and it represents kind of the most real-world attack and the most maybe ambitious of these. And that is, the adversary knows absolutely nothing about your model. He has API access to it, and he can only get sort of a thumbs up or thumbs down. You give it a sample, and it responds with malicious or benign. So let me just briefly run through the related work, just 2 slides in more detail, and describe to you why applying these approaches for PE malware becomes very difficult. And the first is the direct access. So I have the model and say it's deep learning. And the point here is that, for images, I can ask the model, what pixels should I change that would would confuse you the most, and I can change those pixels, and lo and behold, after I modify those pixels, the image is still an image, and that's a graceful process. But if I were to now approach a machine learning model and say, what bytes should I change, or what structure of the file should I change, the recommendation it would give me may, at worst, totally break the PE file format, and maybe at best, destroy the malicious content or behavior of that file. So 2 points here. The attacker here requires full knowledge of the model, and the generated samples may not even be valid. In sort of the second bucket, my collaborators at the University of Virginia have published really cool work on now if the modeler produces a score, they use a genetic algorithm. And you can think about a genetic algorithm, so these are based on evolutionary principles of survival of the fittest. And so one begins with like this population of malware samples, and goes through a series of generations, and every generation a sample gets a mutation of elements of the file that might exist in benign-ware, and that is passed on to the score. And if that reduces the score, then that sample is kept around as a seed for future subsequent generations, right? Now in this process of the genetic algorithm testing against the model, there are some samples, some mutations that break the functionality. And so in order to check against that, my colleagues have put together an oracle. So they check before mutation and after mutation, ensure that the behavior is not changed. And that can be actually an expensive process to run a sample in a sandbox for several minutes, for example. So again, you require some knowledge about the model. You have to get a score, and again, it can be expensive, this oracle. So what we want to do is sort of have it the best of, attack the most difficult and most general problem here, where we don't have full knowledge. We want to ensure we have a valid PE file. We want to avoid having to use any kind of sandbox. The goal here is to design a machine learning agent that can bypass a black box machine learning algorithm that preserves both the format and the function of the file. So I'm going to briefly introduce to you our approach that's based on reinforcement learning by first talking about a game, Atari Breakout. And at the risk of insulting your retro childhood, I'm going to just explain in three sentences. So it's a game, and you have a paddle, and you have 2 actions. You can move left or right, or I guess do nothing at all. And the point is to get the ball to bounce off your paddle and knock down a brick. And if you knock down a brick, you get a reward, a score for that. And so how would you build an AI based on machine learning to play this game? Well, the folks of OpenAI have made this possible for us. I have a link at the bottom. But essentially, you set up this game in an environment. And the environment consists of the paddle and the blocks and some actions that can be used to manipulate this environment. Again, that's move left or move right. And there's some scoring mechanism to detect when a block has been knocked down. And to train an agent, it takes as input this environmental state. And for the Atari game, it's literally like a screenshot of the Atari game. And the agent is supposed to then, given that state of the environment, predict what action would provide the most future reward. And eventually, if some reward is given, that reward is fed back to the agent, and it can learn, hopefully over time, for a given input, what is the best action to do. Essentially, the agent has to play thousands of games, and it's trying to learn sort of this given a state, predict an action. So how does this really work? Now, this is kind of important. I'm going to do it for Atari. It turns out, so let's say that we're going to go through a lucky stroke first, and I choose totally by chance to move my paddle right, and I get no reward for that because no brick was knocked down. I move right again, no reward. I move left by chance, no reward. And I get lucky at some point. I move right, and the ball bounces off my paddle, but again, no reward, no brick. I move right again, still no reward. Eventually, the ball will, goes up and hits a brick, and I get some kind of reward. Now, part of the trick of reinforcement learning is that even though none of these moves in isolation resulted in a useful reward, the sequence somehow as a whole has been useful to the agent. So we distribute sort of that reward back through this action sequence, and by doing this enough times, the agent hopefully can eventually learn to position the paddle in the right spot to make the ball bounce off of it. Okay, so how does this relate to evading machine learning malware detection? All we're going to do is we're going to replace Atari with a new game. And in this new game, the new Atari Breakout board is actually a malware sample. There are a number of actions that we can perform on this malware sample. And there's a new reward mechanism, and that reward mechanism is the machine learning model that we'd like to attack. So the reward looks like this. If I bypass you, you give me a strong reward. If I don't bypass you, I get 0 reward. And it's that simple. Now the agent also, he receives as input the state of the environment, much like the Atari, but in this case, not a screenshot of pixels, but some encapsulation of the modified malware sample that represents the environment. And then again, he chooses an action and gets reward feedback from the anti-malware engine. And the hope is that after playing tens of thousands of games again, eventually, once in a while get lucky and we'll try to learn sequences that bypass this anti-malware machine learning model. So briefly, in our implementation, the state of the environment, I mentioned, is no longer pixels of Atari, but we encapsulate this in a feature vector. And just briefly, the feature vector is just comprised, like in the opening slides, there was file size, number of registry strings. We have about 2,000 of such dimensions that encapsulate header information, section characteristics, imports, etc. And then we feed that into a neural network that chooses that is our policy. So given this kind of state of the world, what should you do? Now our actions are no longer just move left and move right. Of course, we now have a buffet of options to choose from, and to try to make this learning more tangible, not have millions of choices, we've made a design decision, and that is that these actions are somewhat random in behavior. And what I mean by that is that if the agent chooses, for example, to add an import, he can say add an import, but he can't tell you which import to add. That's selected at random from a library of imports known to exist in benign binaries. So you can think about this in Atari, this would be like move right, and it will move right, but the agent has no idea how far, how fast it's moving right. And so that complicates the learning process a little bit. In our implementation, we're going to use the Leaf library, a cool tool from QuirkSlab that allows us to manipulate the binary and write it back to disk in functional form that guarantees the preservation of the file format and the function. Finally, who are we attacking? We're attacking a toy machine learning model in this case. This toy model was trained. It has about, at a 1% false positive rate, it gets about 92% detection rate. And it's based on a gradient boosted decision tree. I'll just note that this kind of model cannot be attacked using the gradient based approaches that I described before. But furthermore, the attacker doesn't really care what kind of model is here. We're just attacking this toy model just as an example. So let's fight. Let me just temper your expectations. The agent has absolutely no knowledge about what it's attacking, only that it's attacking something that will give a thumbs up, thumbs down. He receives kind of incomplete information about the environment that he's attacking. We have this feature vector that's not a perfect representation of the malware. And furthermore, his actions are, hampered and limited. You can think about this, he's like trying to traverse a maze, like without a map, and maybe with kaleidoscope glasses on, and furthermore, he's intoxicated. So this is a really hard learning problem for the agent. Nevertheless, when we train after 100,000 different trials, and we're able to have our black box attack succeed against our toy model on, from virus share samples used as seeds with a 16% evasion rate. So just to make sure that we're not just getting lucky, we also did luck. So for the same samples, we drew at random one of these actions and manipulated it. And indeed, random actually works pretty good. It evades it more than 10%. Nevertheless, our agent is learning some useful concepts that are specific to our model. It is learning how to bypass specifically this model. Furthermore, what's also interesting is that I've evaded our toy model. And if I look at those malware seeds that I used in this game, and I look at their average detection ratio in virus total, 35 out of 62 AV engines caught those original samples. Then I give them to my agent, and he will manipulate them in a way specifically intended to bypass my toy model. However, when I upload those samples, it turns out that they also evade 10 additional AV engines and virus total. So this is driving home the point that even though I am not attacking any of those models in virus total, by attacking my toy model, I have also succeeded in evading some of those in virus total. Now, what do you do against an attack? So I think the state of things is, like most things in InfoSec, is it's easier to be an attacker than a defender in many cases, and sometimes it's more fun to be a pirate than to join a Navy, to misuse a Steve Jobs quote. Two major takeaways. The first is that you can provide feedback to the human from a method like this. For example, in 2 experiments, we restricted our attacks to a class of ransomware samples, and were able to evade with 12%. And the dominant actions that were successful against our toy model were, let's unpack the sample, let's append to the overlay, add bytes to the end of the file that don't affect the file format or function, and then let's rename a random section. And that turned out to be a dominant evasion technique. And further, another example is for restricted to the Verut family of malware. There's a dominant sequence. And you can hand this back to data scientists, engineers, and help them to reason about the weaknesses of the model and how they might fix that. There's actually even an easier approach. And so really simple, all that this process is doing is it's trying to find new samples that the world has never seen and this model has never seen that live somewhere else in this feature space that the model is getting wrong. And all we want to try is let's just feed those samples back into the model and let it learn from its mistakes. Hey, you got these wrong, fix it. As simple as that. We're just appending these totally artificially generated malware samples back to my training set. And in that case, when we retrained our classifier and then re-attacked it with the ransomware attack, the evasion rate dropped from 12% down to 8%. So like a 30% or something decrease in efficacy. All right, I want to just take a big step back and give a big picture about attacking machine learning and some recommendations perhaps. So the first is that if you believe that there are motivated and sophisticated adversaries trying to attack your machine learning model or your scanner or whatever, then it might be a useful thing for you to attack your model first. And to preemptively discover those blind spots and weaknesses in the model. I guess another piece of advice is we've shown that the model we attacked was totally naked. That there was no infrastructure of blacklists or whitelists or any other defensive mechanisms in there. It was just a naked model. And that provides a really easy access point for an attacker. And if for your models, if you can sort of limit the naked exposure of your model in the wild, that can help prevent an attacker from being able to be successful. And furthermore, the thing that I presented today is the hardest of all cases, where there is very little feedback given by the model about whether your attack is successful. Most sequences, again, result in no reward and no bypass, but only a sequence of events finally might result in an evasion. If you present a score, this attack becomes a much easier problem. And I guess another recommendation would be, where possible, you should try to limit the sort of that additional information that you're giving an attacker where possible. So I'd just like to recognize my co-contributors, some of them here at the University of Virginia at Endgame, and thank you for your attention. And I think we do have some time for questions that I'm happy to take.
Is this on? Okay. So the question is that why you are using VirusTotal for tests? Most of the antivirus vendors keep all the good stuff away from VirusTotal. After all, it's only supposed to gather files for antivirus companies, so that's not a good test. And the second question is that doesn't that make the malware really easy to detect? As soon as you use something else than a file analysis, you are generating unique samples and prevalence-based methods will detect them immediately.
Yeah, I think both are 4 points. I think the purpose of today was to demonstrate that the attack is possible. You can actually provide your own data, be it from VirusTotal or elsewhere. So this is just a demonstration of that. But, and the second point, can you mention it one more time?
So the point is that how we detect malware nowadays, it's not by file analysis, because any idiot can defeat that. What we are going to do is that if you are evading static, old-fashioned AV engine, we detect it because you produce unique binaries.
Yeah, and that's also a fair point. I would say that there are a great number of AV vendors that do rely on the static alone classification, and as shown, we're able to evade some of those, even when we're not attacking them directly.
Yeah, but those are only for naming. They are like IOCs.
Perhaps.
Hey, sorry. Can you talk a little bit more about what you think the blind spots actually are? Like, what is causing that?
Yeah, it's a really good question. And the blind spots, I think, really depend on the kind of model that is being used. And let me just take two examples. The one is the model that we used was a decision tree model. And decision tree models can have blind spots because they end up partitioning the space, bisecting the space and during training time, and they say everything in this direction is malicious and everything in that direction is benign. And if there's no data way over there to negate that hypothesis, then we'll believe that. And so it can be sort of overconfident in areas where there's not a lot of data. And so that presents an opportunity in the benign half of the space to find features, find malware samples that are able to live there. And another example is in neural networks, those blind spots are a lot more subtle, a lot more tricky. And it turns out that, as you saw with the bus ostrich example, the blind spots are actually kind of embarrassing for the neural network, I think. And not a lot is understood about why those are. The theory is that it's actually because neural networks are sort of, and we can talk offline, but sort of locally linear. And because of that local linear nature, those blind spots are actually shared across models that share that feature.
Okay.
You use?
Oh, it's a good question. So we trained our agent. We have 2 available in the source code that I should mention that you can all toy with yourself that we're releasing. I'll tweet it out. We released 2 models. One is based on Keras with a TensorFlow backend. My favorite, the one that we used for these experiments, was based on Chainer RL, and it's a reinforcement. It's heavy in the reinforcement learning community.
Cool. Thank you.
All right, I think that's all the time we have for questions. Thank you.